Masanori Morishita. He's going to speak on local symbols and the reciprocity law for foliated dynamical systems.
First of all, I'd like to thank the organizers, Professor Brewer, Lauren, and Ted, for the invitation. I'd like to talk on the local symbol of the reciprocity law of operating dynamical system of three-dimensional manifolds. And as you know, that the theory of Hilbert symbol and the Thames symbol is a very beautiful subject in number theory and algebraic geometry, particularly related to class field theory, as described beautifully by Milham's talk in the last talk. And I'd like to the geometric analog of the local symbol today in the three-dimensional geometry in the context of the Benninger theory. Actually, the last night midnight, maybe today, last night, that I got the email from the Christopher. He saw that my title in this workshop, and he said in the email that it seemed to be related to his talk on the Thursday. So it's just happened. So maybe there are some overlaps, but anyhow, this is my joint work with Yuji Terashima, and it's still being in progress. And yes, in fact, is this question on to find out the geometric analog of the local symbol was first asked by Christopher to me some years ago, and I thought about it, and recently as his student, yes, this is firstly asked by the Christopher, and his student is Janusz the Steltich. They investigated this problem, and he actually gave the partial answer. He introduced a local symbol for the surface boundary of a circle. Our approach is different from him. It's more, maybe more conceptual, and we use some version of the smooth string cohomology. And the higher dimensional the holonomy integral. And these things, these tools, actually it goes back to the pioneering work of the physicist Gavetsky. In his study on the topological action of the two-dimensional quantum field theory, and later studied by the Berlinski. And Gomi and Terashima. So they think it's somehow related to the physics, but I'm sorry that I'm not familiar with the physics at all. So today I just talk about the mathematical aspect of these things. Okay, so let me start with the motivation. So as Mihyun talked about the prime in the ring of integer, it's more generally it's the number ring is the arithmetic analog knot in the three sphere. It's more generally the three manifold. And as Mihyun talked about, we have the linking number of two knots from K and L, because as he said, this, the knot is a null homologous in the three sphere, so we can define the linking number. And we consider the mode 2 linking number, which is defined as a homology class of L homology class of K in the complement or the homology of the complement of L with F2 coefficient, mod 2 coefficients. Okay. Then we have the symmetry of the linking number, as we see easily. Okay. Since the first homology with F2 coefficient is a Galois group of the double cover of the complement of L, so the arithmetic analog of this linking number should be the Frobenius over P in the Galois group of the quadratic extension over the rational, where only one prime Q is ramified. Only one prime Q is ramified. But there is a difference from here between the arithmetic and the topology. The Q, as a prime Q, is not always null homologous in the spec Z. So it's a Q is null homologous in the spec Z, actually the spec Z bar, if and only if the Q is congruent to 1 mod 4 because of the existence of the infinite primes. So in this situation we have the the Gauss reciprocity. That's a symmetry of the Legendre symbols, because this is the Legendre symbol. The Frobenius in this is nothing but Legendre symbol. Okay, so now in number theory we studied the local and idyllic theory for this reciprocity. So local theory, we have the Hilbert symbol. At P and B, at P and A, B at the p-anic number, and ideally, we have the Hilbert reciprocity. The taking all product over the all primes of rational of the Hilbert symbol is 1. If AB is rational, globally rational. Okay. So my question is the question asked by the Denninger is what is the analog of this? What is the analog of this in the three-dimensional topology? Okay. Actually, this question involves one of the most fundamental, most important problem in arithmetic topology. What is it? One of the most important fundamental problem in arithmetic topology is what is the analog of the set of primes, the set of all primes in a three manifold. This is a still open fundamental problem. So if you take the all knots in the maybe three sphere, three manifold, it is too much. It is continuous cardinalities. It is too much. If you take the all knots representing isotopy class in the three manifold, it is still too much. It doesn't have a good structure. But the set of prime has a very marvelous structure, like such a Hilbert reciprocity holds. So it is a fundamental problem to choose a good set of knots in a three manifold, given three manifold. Okay. For this problem, maybe I should note that the recent work of my students, Nivo and Ueki, introduced the notion of the very admissible link. As the analog of the set of all primes in the context in three dimensional, in three manifold, and in his idyllic class field theory. it goes back to the work of the Adam Sikra. Okay, but their theory is purely topological. Okay, but you see, the number field is not just algebraic field. It has a metric analytic structure because it's embedded in the chaotic field and the real and complex number field, as Mifyon talked about that. So it is natural to put the additional structure on the three manifolds, analytic structure on the three manifolds. As one of such approach, the Denninger proposed to consider the foliation, two-dimensional foliation, and the transverse dynamical system. And whereas the set of all primes corresponds to the set of all closed orbit, closed R orbit of the dynamical system. Okay, and as application, he developed the foliation homological study of the Hasselbalch zeta function of schemes. This is the motivation of his work, and actually he deals with any dimensional manifold, any odd dimensional manifold, not necessarily the three manifolds. And also he showed the analog of the explicit formula in analytic number theory. Okay. And also, his student, the Kopai, showed analog of product formula for variation. In the context of the Denninger theory. So along this line of thought, we'd like to introduce a local symbol and show that the analog of the Hilbert reciprocity law. And for this problem, it was stealthy, Janos stealthy. I think he is the first to study this problem. He introduced the local symbol and showed the reciprocity law. For surface bundle. For surface bundles over circle. The surface bundle over circle is a typical, the simplest example of the foliation of the transversal dynamical system is the fiber. The fiber is the leaves. Each fiber is a leaves, and the dynamical system is given by the suspension flow of the monodromy. So he showed this one, but our method is more conceptual. As I said, we use actually our method is maybe an extension of Green's interpretation of a time symbol, of the time symbol on the surface, on the Riemann surface, as the holonomy of a certain complex line bundle, holomorphic line bundle with connection, which is given by the Drinker homology, holomorphic Drinker homology. Okay, so let me briefly review that this interpretation. Suppose we have the Fg is a meromorphic function, and this is a sigma. This is a closed Riemann surface. To P1, it's a meromorphic function. Then, so you know the term at the and take a point in the Riemann surface. Then the term symbol is defined by the ratio of the value at P of the f to the times to the power of the order P of G divided by G to the power of order of f at P. And by the Cauchy theorem, this is undergraduate the complex analysis. This is exponential of the integral 2 pi 1 over 2 pi, the integral over the gamma of the log f d log g minus g of q, and the integral over gamma log d log f. Okay, where is yes, where the gamma is the small circle around the point P, and q is the initial point of gamma. Okay, and we know that this gamma, this small circle gamma, is just boundary of the neighborhood of this point P. And we interpreted this is a holonomy of certain line bundle, complex line bundle made out of f and g with some connection. Here, and f and g, letting x is the space obtained by removing all poles, all zeros, and the poles of f and g. Then that f and g is some invertible holomorphic function on x. Okay, this is h1, the hypercohomology of x to the z1 to the ox. This is the first Dorian cohomology. Okay. Then we take the cup product. If we take a cup product, f and yes, and this f and l and g is given by just cup product of f and g, which is in the h2 of the Dorian cohomology of h2 of x to z2. And it is shown. It can be shown. This is the group of isomorphism classes of the holomorphic line bundle. on X with holomorphic connection. It should be flat because X is one-dimensional. Okay, so this so the term symbol is given by the holonomy of along this small circle of a certain during the co-cycle. Okay. And we generalize this story for the three manifold with a foliation and dynamical system. So let me start. Now it's the introduction is over. So now section 1 is a foliated dynamical system. This cell is due to the Denninger. Okay, the definition. Okay, definition. There's a three-dimensional foliated dynamical system, as called FDS for short, is a pair, is a triple of M and F and Phi, whereas M is a three-dimensional smooth manifold, and we assume, of course, it's connected, related. And F is a smooth, two-dimensional, smooth foliation. It is a partition of the partition of M in the union of the surface, smooth surface, and the Phi is a Russian dynamical system on M, and so that which satisfies the condition, the Phi T is preserves the leads. And it's any R orbit transverse to leaves. Okay, so we make we prepare some notation. Under this situation, we denote by OS. We write this this S for this triple satisfying this condition. Then the OS is the set of closed orbit, which plays a similar role to the set of all primes. And yes, this important thing is omega S is a closed one form defined globally on M, such that the omega S is restricted to the tangent bundle of the foliation is 0, and the value of omega S, the iota Bs of omega S is 1. Is the value of omega S at Vs is where Vs is a vector field generated by flow. And lambda S is this is called a period group. This is an image of the period map with respect to this omega S by 1x by 1m to C. Maybe in general we put this C here. Given by sending the loop gamma to the integral of omega S over gamma. Okay. So here is an example. Here is an example. The first example, this is the simplest example, is surface bundle. So that sigma is a closed surface. And T is a mapping class of sigma. Then M is defined by the mapping torus. So mapping torus. Then we have a projection from M to S1, by which we have the surface bundle over S1 with fiber is sigma. So the leaves, foliation is given by the fibers of F, and dynamical system is just suspension flow of the monotomy. Phi is phi. Okay. So in this case, omega S, we would like to call this omega S. This plays an important role. Masanori is I'd like to call this is a canonical one form. Of FDS. I would like to call this the canonical one form of FDS. Now, actually, the Denninger, the always use this foliation and dynamical system. In his paper, he always liked the foliation and dynamical system. But the giving such data is almost equivalent to giving a closed one form. Okay? But it's not exactly equivalent because closed one form it is not exact. So foliation is given by the kernel of this one form, but it's not always a foliation. So when the omega S is completely integrable, then this condition is satisfied. So it is almost equivalent to giving this FDS is giving a closed one form. So in this sense, I would just wonder that his theory can be maybe described in the somehow it's a Morse theory of attached to this one form. The dynamical system is Morse gradient given by Morse gradient. Anyhow, in this case, omega S is just simply the ds, and lambda S is in this case isomorphic to z. It's not one case. And conversely, if this period group, I'd like to call this as period group of FDS. If the period group of FDS is a Z, then it must be the fiber bundle, surface bundle of S1.